Okay. Okay. Well, everybody has notifications on their screen that this is being recorded now. The tests are in, and we're ready to talk about additional things. I would point out that if I share my screen here, that there are some homeworks that I would like you to look at that we can discuss, I hope, on Thursday in 2 days. And these are works of concerning the law of large numbers. When I was learning this, it always amazed me when you put this stuff to practice that it literally worked. So I would like you to do the following. I would like you to, as it says here, randomly generate points in a square, and inside the square is an inscribed circle. So the circle touches the 4 faces of the square. Does that make sense? Now, if you look at the ratio of the area of the circle to the square, you'll get the probability that if you choose a random value in that square, that you'll hit the circle. So I want you to find out what the probability a point will be in the circle. And I want you to write a computer program to generate random numbers to put points randomly in the circle, in the square. And I want you to keep track of the percent that are in the circle. And then I would like to, I should say percent here. I had total number, but this should be percent. Is percent one word or 2 words? You don't know either. Okay. Let's see if it gives me a spell problem here. So I want you to keep track of and plot the percent of points in the circle divided by the total number of points. Thank goodness for the mute button. And then I'd like you to plot that. And what you'll find out is that as you begin to plot this, that it should approach the probability that you computed in part A. And so you're illustrating here the law of large numbers, that the average approaches the mean. The mean in this case is the probability that you get a point in the circle. And this is what it does finally. Does the limit of your plot approach your answer in A? And again, this is a relatively easy problem, but I think will really illustrate the idea of the law of large numbers and, yes, indeed, how it works. Then I'd like you to look at a couple of problems with the central limit theorem. And this is also computer work. Generate a bunch of empirical PDFs. In other words, I'd like you to go into MATLAB or Python or whatever you use, and generate a bunch of probability density functions. They have to be discrete, but they can be anything you want to. In fact, I think it's kind of fun is to generate a probability density function from a random number generator. I mean, that's a crazy probability density function. The probability density function is going to jump up and down all over the place. But, you can take that probability, you can take that jumping around all over the place, normalize the area to 1, and that will be a probability density function. It's really weird, right? But anything that is non-negative and has an area of 1 or sums to 1 in the case of the discrete is a viable probability density function. And so you can just generate a bunch of those. Then I'd like you to convolve them all. And I would like you to show that indeed the approaches a Gaussian probability density function. In fact, plot over top of your empirical results the corresponding probability density function, Gaussian probability density function that it's attempting to calculate. And I think you'll be amazed. And again, do you understand what I mean by using a random number generator to generate these crazy probability density functions that just go up and down? And you would think that if you generated 10 or 20 of those and you convolve them, that you would get something crazy. No, you get something quite smooth, and that smooth thing is a probability density function. So you can use whatever you'd like. You can use any sort of probability density function that you would like. So first thing I'd like you to do is after you do the convolution, and by the way, I know in MATLAB, there's a CONV operation that does the convolution for you. So you don't have to take Fourier transforms and multiply an inverse Fourier transform. There's literally a convolution, I believe it's CONV, that lets you do the convolution right away. So this is a very simple problem. And then plotting the convolution and the approximated Gaussian in the same figure. And you'll find out that if you do 10 of these, even these crazy probability density functions that we talked about, you are going to get a result that is astonishing. Astonishingly close to, excuse me, I'm adjusting volumes here. It's astonishingly close to a Gaussian probability density function, instantiating our proof of the central limit theorem. And then I'd like to give you an example. Say that we are adding up a column of dollar figures and we round them up. Now, so we're not rounding them to the nearest dollar. We're rounding up. We're going to the ceiling operation, if you will, of whatever it is. So $1,000.01 would go to the $1,001. And $50.10 would go to $51. So it's rounded up in every case. And so there's an error associated with this rounding, and you can estimate that error with the probability density function. So I would like you to estimate the probability that the rounded sum is greater than $100. And I would like a number here, okay? You should be able to look at your ERFs, your error functions, and give me a number. And then I'd like you to know what the error was if it's greater than $1,000. Okay, any questions? Yeah.
On that one, when you say rounded sum, do you mean the summation of the amounts you rounded by?
Yes.
Okay.
Okay. Okay, so that probably the sum. Okay, I started a bunch of sentences here. Okay, how's that? That's probably better wording.
That could still mean, you know, do the $1,001, sum those up. But I think we all understand what it means now.
Let me do this. I'm going to make it easier. Just going to put errors in there.
That's good. Yeah.
Okay, so I think that that's going to make it easier. Yeah. Okay, great. So yeah, let's, I think these are all very straightforward problems. And my hope is that when you do them, you'll look at it and you'll go, wow, that's really cool that all of this mathy stuff that we derived literally works. And so you can see it in practice and see it working. Okay, any questions at all? Okay, good. That means I'm very, very clear and everybody understands me, or I'm very obfuscated and nobody understands me. So I hope it's the former. Okay, let's look at this then.
Dr. Marx?
Yes.
I have a question for the last problem.
Okay, is it a problem which reveals the answer?
Yes.
No, don't ask it then.
Okay, thank you.
Okay. Okay. Yeah, Glauco gave away the answer, I think. Anyway, we'll see. Okay, last time we were talking about stochastic processes, and we said that in order to totally characterize any stochastic process, you need to know things like the first order statistics. What's the first order statistics? That's when you just look at a single point in the stochastic process. A single point in the stochastic process is a random variable. But you know that one of these random variables might be related to another random variable. And And that's something that we need to take into account. So therefore, we go into second order statistics, where you take two numbers, and these numbers are at t and tau. And if you give me a t and tau, I can generate something called the autocorrelation function. And this is the same autocorrelation function that we've seen before, but it's the expected value of the random variable at t times the random variable at tau. And notice that if you change either t or tau, you're going to change this expected value in general, won't you? Right? If I chose the value of t over here, I might have a different autocorrelation function. So this is for a specific value of t and tau. And correlation tries to tell you that how the random variables are related in some sort of sense. And then related to that, the autocorrelation is like the second moment, and more useful, or not more useful, but something that we use quite a bit is the autocovariance, which is the autocorrelation minus the product of the means. So this is just like the variance, where we take the second moment and we subtract the square of the mean. You remember that? This is analogous to that. So these are definitions, and we're going to unpack these and see what happens here. So let's look at some special cases. One of the special cases is the so-called autocorrelation. The autocorrelation is when you have, as you see here, tau is equal to t, right? And if we go to the previous screen, if t is equal to tau, we just get the expected value of x squared, right? So that's exactly what we get here, is the expected value of x squared. Now, here is a very important engineering application of this. If you stick your fingers in the socket, in the power socket, what are you feeling? You're going to feel a sinusoid, right? A 60 hertz sinusoid, correct? And so you touch the socket, you stick your fingers in the socket. What is the mean value of this? Can you just tell intuitively?
0.
Yeah, it should be 0, right? Okay, so you stick your fingers in the socket. Do you feel the mean? No, you don't feel the mean. If you felt the mean, you wouldn't feel anything. Okay? What you feel is the autocorrelation. Why is that? Well, let's take an example. Let's take a 1 ohm resistor. And I'm going to use this for current. This is an electrical engineering course, so I better draw a resistor somewhere, right? Let's suppose that the current which is being fed to the resistor is a stochastic process x of t, right? What is the power associated with the power as a function of time associated with the resistor? It's equal to the resistance times x squared, right? As a function of time. So that's the instantaneous power which is dissipated by the resistor. And we're kind of saying here that this is 1 just to get rid of some unnecessary details. So here's the point. The expected value of the power that is dissipated by the resistor is equal to the expected value of the square of the stochastic process. Does that make sense? So therefore, the autocorrelation is very important in engineering, because that's what gives us the power, for example, in circuitries. You could do the same thing for voltage, where the applied voltage was a stochastic process. But in both cases, the instantaneous power is equal to x squared bar. And so what we would have to do is we would have to compute the second moment of the stochastic process in order to figure out what the average power we were getting. So x of t x of t is equal to something like a times the cosine of omega t, correct? And we can put in here a phi to make it stochastic. What is omega? It's 2 pi times 60 hertz, right? It should be pretty close to 2 pi times 60 hertz. What's the amplitude? What's the amplitude of x of t up here?
120 volts.
Is it 120 volts peak?
I believe so. Yeah, I could be wrong.
Okay, I don't know, but here's the interesting thing. Nothing in here is stochastic. Omega is not stochastic. The amplitude is not stochastic. It's something we don't know, but the phase is stochastic. We don't know what the phase of that current is, correct? So the phase is going to be uniform on, say, 0 to 2 pi, right? And if we do x squared, that's equal to a squared times the cosine squared of omega t plus phi. And the expected value of x squared. Now, this gets a little funny, and you'll have to work around this. We're so used to integrating over things like time and frequency. But here, what are we integrating over? To do the expected value, you have to integrate over the random variable. The random variable here is phi. So we have to do a squared times the cosine squared. And we want to integrate from, say, 0 to 2 pi. Cosine squared of omega t plus phi. And notice this is weird. We're integrating with respect to the random variable, not with respect to time. When you first see this, you think, "Ooh, I should integrate with respect to time." No, but when we take the expected value, and this should be a squared over what, 2 pi, right? Because this random variable, I'm squeezing too much in here. This random variable goes between 0 and 2 pi, and therefore should have a value of 1 over 2 pi in order to give it an area of 1. Correct? So I need to put the 1 over 2 pi here and integrate from 0 to 2 pi. So what is the area? What is the area? Wait, is this right? Yes, let's see. Yeah, so what is this integral equal to? Can anybody tell me? Well, anyway, whatever this integral is equal to, cosine squared is a function of phi. I want to say 1/2, but I know that that's wrong. But anyway, if we compute this value, we can actually then find the power which is delivered when we get the result. Okay. I think Adam.
It's pi.
It's pi?
Mhm.
Ah, okay. So the value is a squared over 2. Thank you, Adam. A squared over 2. Now, you know why this is kind of cool? Do you remember from circuits class where you have a sinusoid and do a over root 2? Do you remember that? Where we talked about the so-called RMS value of the sinusoid? That's exactly what we get here. So if we get the square of the moment times the square root of that, which in our case is going to be the same thing as the standard deviation. Why is it going to be the standard deviation? Because the mean is equal to 0, correct? So the mean and the second moment are both equal to the same thing. So this is the standard deviation of the of the stochastic process. So you might remember back in circuits where they talked about the RMS value of a sinusoid. We've just kind of derived it here, haven't we? That's the RMS value. And if we square the RMS value, what do we get? We get the average power which is delivered. The average power which is delivered is equal to A squared over 2. So when you stick your fingers in the socket, that's what you feel. You feel the magnitude squared, well, you feel the power of A squared over 2. Okay? So that's the reason that the autocorrelation is so important, is that it relates very nicely to power. Many of you have heard of the concept of the power spectral density of a stochastic process, and it turns out that this autocorrelation is related to that, and we'll see that very soon when we talk about that. Okay, the corresponding value, if we take the autocovariance, what was the autocovariance? The autocovariance was this thing down here, right? Where'd it go? That was the autocovariance. So now we're going to evaluate this at t. And so when we do that, we get the variance of x of t. So the variance of x of t is, or the square root of it is sometimes referred to as the volatility of the stochastic process. Let me give you some examples here. This is one stochastic process. And let that stochastic process be kind of like this. And here's another stochastic process. And that stochastic process is going to look something like this. It's going to be much smoother. Now, if I look at these stochastic processes, just eyeballing them, here's the way to think about it. Just eyeballing it, it looks like the mean of this stochastic process is about here, right? The mean tells you roughly where it's centered. Does that make sense? And I'm assuming that the mean doesn't change with respect to time. Here, this is y, and we probably have y is, we can have the mean of this stochastic process equal to the mean of this stochastic process. Is that okay? They're different stochastic processes, but at least they agree in the first moment. Now, the thing is that this stochastic process here moves up and down a lot more than this stochastic process. The manner that it moves up and down is going to be the, let's call it the sigma. That's going to be related to the square root of the autocorrelation. So this is the sigma of x, and the sigma of x is broad because we know that this random variable, as it goes up and down, goes over a lot of values. Whereas down here, the standard deviation, the going up and down, is going to be so smaller. So this is the sigma of y, which is going to be less than the sigma of x. So if we have a stochastic process which doesn't change with respect to time, then it turns out you can have stochastic processes with the same mean, and you very much with a different sigma, with a very different oscillation, if you will. By the way, in the stock market, they call sigma equal to the volatility. Have you heard of that term in the stock market where the market is very volatile? It means that the stock market, the tick prices are going up and down really large. If you have low volatility in the stock market, that means that the tick prices are changing relatively slowly, okay? That there's not a lot of up and down movement. So this is the measurement. This is the measurement. The variance of x of t is the measurement of the volatility. That's the measurement of the volatility. And the mean is, again, kind of the average value. I always think of the mean kind of as follows. If you took the stochastic process and you pretend it was made of ice and you melted it down, what would the water level be, right? If it was made of ice and you melted it down, what would the water level be if you put it in a container and melted that ice down? We're assuming now the ice doesn't expand or contract. You get the idea, but that's a good way to think about it. But notice this is only applicable when you have a stochastic process, which is something we will later call stationary. We will give a very nice firm definition of stationarity shortly. But the basic idea is if you have a stationary stochastic process, it doesn't change with respect to time. You could have non-stationary. An example of this, for example, is suppose that I have an antenna up and I have an arcing light switch. And every time I turn on the light switch, I found out that my antenna picks up something that looks like this. By the way, are you hearing echo of me? Okay, everybody has their microphone off. Okay, I think somebody had their microphone off. So if you flick on the light switch and your antenna might receive this for the first time, say this is X sub 1. And it might receive some X of 2 if you go over and you repeat the experiment and you turn the light side, or you switch the light, hit the light switch again and it arcs and you generate another antenna pickup, which is X of 2. Notice that this is an example of a non-stationary process in the fact that steady state, it's equal to 0, but you have a transient sort of effect here, correct? Now, you can still apply this idea of instantaneous power and such. You just can't think of it as a stationary process. If you think of stationary processes, you can think of a lot more interesting things to do than a non-stationary process. But we'll visit this. And what I want you to get from here is the idea that the second moment is related to the power. The second moment is related to the power in engineering applications. Wow, I'm sitting back and looking at this. I put a lot of information on this little slide, didn't I? Then there's something else called the correlation coefficient. This is related to the covariance. And this is the correlation coefficient. This is the thing that statisticians like to do when they plot their X and Ys. They like to figure out what the correlation coefficient is. And so it's as you can see here, the correlation coefficient is equal to the auto covariance divided by the normalized, if you will, by the individual standard deviations of the stochastic process. And you know about correlations. You can be totally correlated, totally uncorrelated, or something in between. So the correlation itself must lie between -1 and 1 at all times. You're either correlated or you're not correlated, or if you have 0 correlation, that means you're uncorrelated, and one kind of has nothing to do with the other one. We won't deal too much with correlation coefficients in this course, but I do want to point out that this is an extension of the autocovariance in terms of its definition. Let's take an example. It's always good to have an example. X of t is equal to a times the cosine of omega t. Now, what makes a process stochastic? A process is stochastic if there's anything of a random variable associated with the process. Here we have a stochastic process and we have 2 random variables. We have the random variable A and we have a random variable omega. We're going to assume that they are independent of each other. So we will assume that the amplitude is normal. The amplitude, is normal on 0 to 1, and that sigma, which is the frequency, is uniform on 0 to 2 pi. So that's the assumption we make, and we're going to make the assumption that A and sigma are independent. So therefore, we're going to have a bunch of realizations of these. There's the probability density functions. We're going to have a realization of a number of these, and we showed these to you earlier last course. Let me go back up here. No, I guess it wasn't in these slides. But you remember we showed you a number of instantiations of this random variable. I showed you a plot of it. So sorry, I thought it was in this lecture. It's in the previous lecture. So what are the expected value, and what is the what is the autocorrelation of this stochastic process? Now notice again, for general, we not only have to do the second order statistics comparing t and tau, but we would have to also, if we wanted to totally characterize the random process, we would find out that we'd have to do t, tau, epsilon, and a bunch of other points on the line, right, in order to get the multidimensional probability density function to characterize it. We'll find out, and this is really cool, we'll find out that many engineering applications that all we need is the second order statistics. It isn't obvious yet, but we will find out that we only need two random variables, the second order statistics, if you will, in order to characterize the stochastic process. This allows us to get to things like the autocorrelation, and later when we talk about the power spectral density, it's enough to get us to the power spectral density too. So that's the reason we're concentrating at this point on comparing two random variables at t and tau. So let's go ahead and figure out what this is. Both the amplitude and the frequency are random variables, and those are the random variables. And let's first of all compute the mean. Now, when we compute the mean, I remember when I first learned this, it was kind of weird. This is our random variable here, and this is our random variable, right? So when we do expected values, we are going to integrate over A, and we're going to integrate over omega. We're so used to integrating over time that it's hard not to integrate over time, but we're not integrating over time. We're integrating over the random variables in order to get the expected value. So here's the simple math. This is equal to the expected value of A times cosine theta. A times cosine of omega t. So here is the function, right? And we want to multiply it since they're independent. The joint is the product of the marginals. So here is the product of the marginals, f sub omega. And we can break up the integration, and we can just integrate over, first of all, the amplitude. And so we're going to substitute in the amplitude, we're going to substitute the probability density function for this. Something here says, no, I guess we're fine. So we're going to substitute in the probability density function. Now this is a Gaussian probability density function. So if we look at this as a function of A, it's going to look like this, right? If we look at the integrand with respect to A, we are going to get A times the density function. If this is the density function for A, the density function A times f of A is going to be what? It's going to look something like this. Nope, it's going to look something like this. Do you agree with that? If we multiply this density function times A, which is this line here, we're going to get something like this double dipping curve. And the point is just going through this, to this mental exercise, we can see that this is equal to 0. Simply, and it's the same thing, this original density function has a mean of 0, and essentially we're computing the expected value of the random variable, which is the mean of the random variable, which is 0. So therefore, this whole thing goes to 0. Just by looking at the fact that the integrand is odd, an odd function, if you remember odd functions. So therefore, this goes to 0, so that means we don't even have to do the second integration, that the whole thing is 0. And this makes sense. Yeah, kind of a sanity check. If you do A as the amplitude here, and I don't care what omega is, you know, omega could be really, really big. You're going to get a stochastic process which has a mean, of 0. Think of the ice analogy. Here we have negative ice, but we're just as much on top as we are on the bottom, and all the tops and bottoms cancel themselves out, and so we're left with a total expected value of just 0. Let's do the autocorrelation. This is a little bit more picky. Okay, let's first of all, we start with the definition of x of t and x of tau. This is the definition. In fact, we could put a little is equal to by definition notation here. And so what is x of t? That's a cosine omega t. What's x of tau? That's a times cosine omega tau. So those are the two random processes that we're talking about. And the value of a in both cases is the same. So we have the expected value of a squared, since we have two a's, and then the expected value of the cosine of omega t times the cosine of omega tau. And since the random variables are independent of each other, we can break out the expected values into the product of the expected values. So we know that the expected value of a squared is going to be equal to sigma squared. It's going to be equal to whatever we've already computed this, right? We've computed the RMS value of a sinusoid. So it's going to be the same thing. It's going to be the standard deviation. It's going to be the standard deviation of the Gaussian random variable, right? We have a zero mean Gaussian random variable. And we know that the mean is 0, and we know that the variance is therefore equal to the expected value of x squared. So the expected value of x squared there is nothing more than the standard deviation of the Gaussian random variable. Then we're left with this part. Oh my goodness, what does this mean? Okay, I don't know what it means, but we have to take this whole thing, and we have to integrate from, say, 0 to 2 pi. The probability density function has an amplitude of 1 over 2 pi. And then we put this whole thing d omega. So we just substitute this whole thing into the integrand there, and we perform this integration. So that then turns out to be the integral we have to do. If we do this, and I'm not going to do it because it's just a bunch of simple calculus, we come up with this result, which has no particular intuitive meaning to me, but that's the result that we get. Okay, so that would be the cross correlation. By the way, this should be cross correlation, right? The autocorrelation is when x of t is equal to, or t is equal to tau. We're going to get to that for a second. So the autocorrelation of x of t, let's look at this. When t is equal to tau, oh boy, I changed that and I should change it back. When t is equal to tau, what is this equal to? Some of you might say 0, but it isn't equal to 0, right? And I've made a mistake here. For very small values of theta, sine of theta is equal to theta if theta is very, very small. Have you seen this approximation? That's the first term in the Taylor series. So my point here is that applying L'Hopital to this point, if t is very close to 0, then this is very, very close to 2 pi t minus tau. In the numerator, and in the denominator, it's equal to t minus tau. Is that okay? So again, for the numerator, I said that, okay, for very, very small arguments, that is t is equal to tau plus a billionth or something like that, that the sine of 2 pi t minus tau is the same as 2 pi t minus tau. The denominator stays the same, so this goes to 2 pi. So this goes to 2 pi when t is equal to tau. And I made a mistake, and I'll correct it and download it or upload it to the slides. But this, if we look at t is equal to tau, we should get this. And what I did is that should be a plus 2 pi here. This is funny. I was quickly reviewing these slides for the presentation today, and I thought, okay, this thing, this big ugly thing here, this goes to 0 because the numerator goes to 0, and I didn't recognize that the denominator also went to 0. So I changed it. So I was right initially, and I made the incorrect assumption. So what we're going to get then, when t is equal to tau for the autocorrelation, we're going to get this is t. We're going to get sine of 2 pi times 2t, and this is 2t, and that's exactly what we get. So this is just going through the results and turning the crank of what we're doing. And so this is what the variance of x of t is equal to for this stochastic process. This is what the autocorrelation is equal to. Okay. Now this is interesting because the autocorrelation the variance is a function of time. Usually when you think of a sinusoid, you have a function, you don't think of a function of time. But notice something here. If I look at a bunch of instantiations of this stochastic process, I will start out with one sinusoid with a certain frequency. And then I will start out with another sinusoid with another frequency. But the interesting thing is that I'm always going to start out with an amplitude greater than 1, right? Now, I guess the amplitude can go negative. Okay, I stand corrected. So the amplitude can go negative here too. So we could have another sinusoid that looks like this, right? So we have all of these different sinusoids. And it turns out that as you get out here, as you get out more and more and more, that you're going to have a stochastic process which is different. You're going to have a different stochastic process than you do here. And if the second moment is a function of time, you have a non-stationary stochastic process. We will define again stationary as something which doesn't change with respect to time. But this certainly changes with respect to time. If the variance changes with respect to time, the stochastic process changes with respect to time. How do we compute these things empirically? We go into the lab and we get some sort of stochastic process here. Say, for example, this stochastic process here. And this stochastic process is going along, and I don't know, what's its mean? What's its volatility? What's its autocorrelation? How do we compute this empirically? We compute it empirically using the law of large numbers. And there's different instantiations of this. I'm about to show you something which is called the Ensemble Average. The Ensemble Average, say, for example, to compute the expected value of x of t, is simply equal to a bunch of realizations of the stochastic process. In other words, you have to repeat the stochastic process a number of times, right? So here we've repeated it. Here's another instantiation. We have a number of them, right? So these are all stochastic processes. These are just like samples from a random variable. In order to get the mean at a point, we would take, say we wanted the mean at this point, at this value of t, we would go down. And if we had these ensembles, we would simply take the average of all of the numbers that we got here. And this is essentially what this is saying. We do X. Now, this is a little bit different. The notation is a little bit different. We're going to use this to mean that the stochastic process that we're measuring is potentially a function of time. But anyway, what we do is say we have 9 values here. So n is equal to 9. So we have 9 values, 9 examples of the stochastic process. We're going to take them and we're going to average them together. And in doing that, if we average 9, we get this. We get this result. Okay, what happened to my writer here? Okay, there it is. We get this result. If we were to take 100 of these, we get this result. Now, it turns out that this was generated with a random number generator that was uniform between 0 and 1. So I just took, I believe this was a MATLAB program. I did the RND and I just generated a bunch of random numbers between 0 and 1. You can see that in each case that the stochastic process went between 0 and 1, right? So if it went between 0 and 1, it was uniform. What is the average? The average is equal to a half, correct? And so if we average 100 of these, we get something in each case that is pretty close to a half. And so we're applying, if you will, the law of large numbers here. We're applying the law of large numbers to estimate what the expected value of the stochastic process is at every point. Now, at this point, all of the random variables are the same, but they need not be to apply the ensemble average sort of idea. Now, this also extends to things like the variance. If I was to take the previous result, and now I'm going to take this stochastic, what happened? I'm going to take this stochastic process. I'm going to take this first stochastic process. I'm going to square it. I'm going to take this stochastic process. I'm going to square it. I'm going to take this one. So I'm going to square all of the stochastic processes. And then I'm going to average the square of all of the processes. And that should give me a good estimate to the second moment if I average the square. And that's exactly what we do. We can average the square of all of these stochastic processes. And what is that going to give us roughly? That's going to give us the expected value of the square, right? Then if I take that and I subtract the estimate of the mean squared, I'm going to get the variance at every point. So I've done 2 averages. I've averaged the actual sequence and I've averaged the square of the sequences. And if I do this for 100 values, I get the curve, which you can see here. Now, it's not too informative until you realize that a random variable with a value between 0 and 1 has a variance equal to 1/12, as it has down, as you can see down here. So this should converge, according to the law of large numbers, to 1/12, which is about 0.0833. And you can see that kind of looks like 0.833, right? So it does work. The ensemble average does work. So this is point statistics. These are, if you will, one random variable at a time. We're not comparing 2 random variables side by side. So I want to go back up here. Whoops, wrong way. And recall the autocorrelation. And I want to do the autocorrelation here for the expected value of x sub n times x sub m. And I'm going to assume that these processes are IID. If they're IID, if all of these samples are IID, then the autocorrelation is equal to the square of the mean for n is not equal to m and is equal to a squared for n is equal to m. How I can show that very easily. Because if I'm going to do it now. If n is not equal to m, this is equal to n is not equal to m. This is the same thing as the expected value of x sub n times the expected value of x sub m. Because if they're independent of each other, the expected value of the product is the product of the expected values. And so that's what we're saying here. Both of these are equal to x bar, which is why we get the a bar squared for n not equal to m. If n is equal to m, what do we have? We have the expected value of x sub x squared of n, which is equal to the second moment, right? If n is equal to m. And so that's the reason that we have here. That's the result that we have here. So this is all well and good. And so this is what we have if we have IID points. By the way, we'll find out later that when you have IID points, that you can consider this in many cases as an instantiation of so-called white noise. White noise is where you have independence or non-correlation among adjacent points. The autocovariance, on the other hand, is equal to, well, let's see, it's equal to 0 for n is not equal to m. It's equal to 0 for n not equal to m because we subtract off the square of the first moment, so we get 0. And if we subtract off the square of the first moment here, we get the variance of a. So therefore, we should get in this response something that looks like this. This should be our autocovariance. I'm sorry, our autocovariance. It's equal to the variance of A times the Kronecker delta, which is the diagonalization tool. So if we were to look at the autocorrelation of n versus m, n is going this way, m is going this way. If we're to look at the autocorrelation of n and m, we should get we should get the variance of A equivalently when n is equal to m, and we should get 0 elsewhere. So if we were to place this autocovariance, this two-dimensional autocovariance, as a matrix, that matrix would be a diagonal matrix. So let's skip down here and talk about generating this from data. How would we generate this autocovariance or autocorrelation even from empirical data? Well, here again, we have one of these results. And this is a stochastic process. We're going to assume it's IID. Now, the outer product of x of t is equal to x of t times x of tau. What does that mean? Well, it means what we have here in the next. It looks terrible, but here what we have is we have kind of an x of t. So we have t going in this direction. Here we have an x of tau. So tau goes in this direction. And so we put the vector x of tau here and the exact same vector x of t here, and then we smear them back across and multiply them at every point. And we kind of get this field of grass here. No structure. You can see no structure in a simple instantiation, right? So this is one example of x of t minus times x of tau. Now, if we were to do this for a bunch of realizations of x of t, if we were to do it for a bunch of realizations of x of t up here, and we were to average them together, what should we get? We should get the eventually the autocorrelation or autocovariance if we subtract off the mean, if you will. So let's do that. What happens if we do this and average out a bunch of these things to first of all compute or estimate using the law of large numbers the autocorrelation as a function of t and tau? So we take this kind of field of grass, if you will, and we average a bunch of them for different results. And then we can subtract off the means that we have also computed from this result. And if you do that and you do enough of them, if you do just 100 of them, this is the result that you get. So if you take those, again, grassy fields that we had up here, if you take these grassy fields and you generate 100 of them and you average them together, you get this relationship, which is exactly what we promised. It would be a diagonal relationship, okay? So hopefully this gives you an intuitive idea of generating some of these first and second order statistics given empirical results. Any questions at all? So far, good? Okay. So I have one correction to make on that. I have to make sure that I make that correction and upload it again. So let's talk about some different random processes here. And this is the new slide deck, if you will. You recall the Gaussian probability density function. This is something which is going to become very, very important in engineering. Many of you have probably heard of the term white Gaussian noise or Gaussian noise. How many have heard at least the term Gaussian noise? Okay, so we're going to get into exactly what Gaussian noise is. And how many have heard the term white noise? I think the average person on the street has heard of the idea of white noise. And what does it mean for white Gaussian noise? So that's what we're going to talk about. Well, let's first of all recall the multivariate Gaussian probability density function. And this is for n dimensions. And this allows correlation. So this K is the correlation matrix. This is the correlation matrix. And you know that estimation that we just made, which was the correlation of those fields of the grass fields, that was an estimation of the correlation matrix. That was the estimation of the correlation matrix. So we can generate this empirically. We can generate the means empirically, and therefore we can talk about this for n dimensions. And let's see, do we have? No, we don't have a dimension. Yeah, we do have a dimension. A dimension is n. So for a dimension of n, we have n random variables, and the K matrix is the covariance matrix is going to be an n by n matrix. So if for all n, the corresponding PDFs are Gaussian, then the random process is Gaussian. Huh? What does that mean? That means as follows. Suppose you have a stochastic process like this, right? This is an x of t. If you take a point here, a point here, a point here, and a point here, you will get there's 4 points here, right? You will get a 4-dimensional Gaussian probability density function. If you take a point here, let's see, can I change colors here? I can change colors. Okay, say we took a point here. That isn't a very good change, is it? Let me try green here. If, on the other hand, we take a point here and a point here, that would be a two-dimensional Gaussian random variable. If we take a point here, 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 we would have 1, 2, 3, 4, 5, 6, 7. We would have 7 random variables if we took those 7 points. If that is if the underlying probability density function describing this is a 7-dimensional Gaussian probability density function, then that's good. And the point is, I don't care how many points you choose. I don't care what n is. If you sample this stochastic process at n different points, then that underlying stochastic process is, or the underlying random variable, multidimensional random variable, is Gaussian, and it fits this distribution. We've already seen that the Gaussian is kind of our friend, right? You know, in the central limit theorem, everything goes towards a Gaussian. It's just a wonderful, it has some wonderful, wonderful properties. And it turns out that this definition is important in useful in signal processing. So again, let x sub k equal to x of t. So this is a sample of the stochastic process. We choose any value of n that we would like. And if for all n, for no matter what your choice of points are, the corresponding probability density functions are Gaussian, then the random process is called Gaussian. So if we say that a process is a Gaussian random variable, this is mathematically what we mean. Okay. Huh, I can't get off this page. What's the deal here? Okay, it looks like my screen is frozen for some reason. I'm hitting the escape button. Oh, you know what? I should probably just stop sharing. How does that work? Okay, and then let me share again. Okay, well, it didn't like it. Okay, I'm going to unshare, and then I'm going to see if I can dink around with the slides. My screen is totally frozen.
You should try doing Control Alt Delete on your keyboard.
Oh,
and
to
then
go to
killing
the
PowerPoint.
task thing. Yeah. Okay, I'm not sure. I hope you haven't lost me, have you?
No, sir.
Okay. Okay. Well, that's good. And I have not lost you. Okay. I think I did. I think I did something. I'm not going to go to full screen on the PowerPoint again because something happened. Okay. We're going to go to a totally unrelated theorem right now, which we're going to use later. And we'll probably end up the lecture there. This is something called the Flip Theorem. The Flip Theorem says you have any stochastic process, right? You have any stochastic process, x of t. And the stochastic process has a mean of m of t and an autocorrelation of r sub x. Here's what we're going to do. We're going to flip a coin. And if the coin is heads, we're going to call it a 1. If the coin is tails, we're going to call it a -1. And if it's -1, we're just going to multiply by, okay, I probably can't do exactly. But if it's -1, y is going to be equal to -x. So y is equal to -x with a probability equal to 1/2. And it's equal to y is going to be equal to x with a probability of half. So again, we take an arbitrary random variable or stochastic process. We're going to flip a coin. +1 is +1, +1 is heads, -1 is tails. If it's tails, then the new stochastic process is equal to minus the first. If it isn't, then it's exactly the same stochastic process. Now, if you flip a coin, it turns out that the expected value of y is going to be 0. Because if you look at this, y of t is equal to a times x of t. A is a random variable, correct? And a is the random variable that you get by flipping the coin. It's either a plus or a -1. And so the expected value of y, is equal to the expected value of a times the expected value of x. And I know that the average of my coin flip is 0, correct? The average of my coin flip is going to be 0. So it doesn't matter what x of t is, the result is going to be exactly the same. The other thing is that if y of t has mean 0, y of t has exactly the same autocorrelation. It has exactly the same autocorrelation as the original function. I was trying to talk and change my color at the same time, which isn't working. So what I'm maintaining then is that r sub x or r sub y, that is of the flipped result, is the same as r sub x. And you can choose this very easy. R sub y is equal to, well, let's see, that didn't work very well. R sub y is equal to the expected value of x of t, or y of t, times y of tau, right? Which is exactly the same thing as the expected value of a times x of t times a times x of tau, right? Which is equal to the expected value of a squared times the expected value of x of t, x of tau. Now, what can a turn out to be? A can turn out to be 1 or -1. What's the expected value of a squared? It's going to be 1, right? A squared is always 1. It's -1 squared or 1 squared. So this is exactly the same thing as the autocorrelation of r sub x. So again, the basic line between in the flip theorem is that if you take a stochastic process and you flip a coin +1, -1, that the mean of the new stochastic process is always 0, number 1, and number 2, that the autocorrelation stays exactly the same. So the mean goes to 0, the autocorrelation stays the same. So we'll use this later on. This is kind of a lemma that we're going to apply. So I think probably this is probably a good place to leave the lecture. So with that, are there any questions? Any questions at all? Okay, I think then that what I would like you to do is to look at the homework. I think the homework is pretty straightforward. See if you have any questions on Thursday, the next time we meet. And if not, we'll just go ahead with the lecture on different aspects of stochastic processes and trying to characterize them. To date, we have looked at just the first and second order statistics, and we've done a definition. We just defined the Gaussian stochastic process, which is probably the most commonly used in engineering because of its tractability. There's certain things you can do with Gaussian probability density functions that are just astounding. There was a Nobel Prize won for something called the Black-Scholes equation. The Black-Scholes equation was the first to analytically describe options pricing on the market. You familiar with options pricing or options, what options are? Kind of like, okay, here's the thing. I have 100 shares of, I have, let's not even say 100 shares. I have $1,000 worth of Boeing stock and I want to insure it. So I come to Glauco and I said, you know what? I want to buy an option from you that I can force you to sell my Boeing stock for $1,000, but we're going to do it in a month. And so whatever happens on this day, a month from now, I can force Glauco to buy all of my stock for $1,000. It's $1,000 today. I don't know what it's going to be in a month. Now, if I get to a month from now and the price of Boeing stock is at $1,200, if it's gone up quite a bit, I would be stupid to sell it to Glauco for $1,000, wouldn't I? So I would not exercise my option. However, if the price of my stock went down to $800, I would come to Glauco and said, "Man, we had a deal. You got to buy these from me." And he bites the bullet, and because of that contract was made, even though they're only worth $800, he has to buy them for $1,000. So I have exercised my option to sell to him. Does that make sense? So here is the question: what is a fair price that Glauco's selling me insurance? What is a fair price that he should charge me for this option? Should he charge me $10, $100? What's a fair price? Right? And there were a couple of guys, Black and Scholes, with the help of Robert Martin, who developed a mathematical theory which showed that options pricing could be derived analytically. So they came up with a formula for it. They won a Nobel Prize for it. I think one of them had passed away, but two of the three won a Nobel Prize. I think you have to be alive for the Nobel Prize. But here's the thing. In order to derive the result, they had to make a Gaussian assumption on the way that the stock market moved. They had to assume that stock market was Gaussian. Why did they have to do it? Because the Gaussian is our friend, man. Every time you get a Gaussian, you go, oh boy, there's lots I can do with this Gaussian. You have the central limit theorem. You have this model of the stock market. We're going to get into Brownian motion and all sorts of different things where the Gaussian is applied. And like we mentioned, people have heard of white Gaussian noise. Well, it turns out that the stock market is not Gaussian after all. If you look at the tick data, it's not Gaussian. The Gaussian kind of comes down like this. It turns out that the stock market has much broader tails than the Gaussian. But nevertheless, just the beauty of their result won them a Nobel Prize. So that's an example of why. That's an example of one of the places where Gaussians are so useful. Another place is Brownian motion, or random walk. In fact, this was one of Einstein's papers in his miracle year, I think, of 1904, where he published 4 remarkable papers. One of them was on Brownian motion, which showed that if you put a little piece of paper, itty bitty, in like a fluid, you could see it bouncing around. And this was the molecules that were hitting the paper. And as the water molecules hit the paper, they kind of jarred it around in random sort of fashion. And during perestroika, I remember that some of the trading houses on Wall Street were very interested in hiring the Russian physicists who couldn't get a job in post-communist Russia. And the reason they couldn't get a job is that the economy had collapsed. But it turned out that they knew a lot about Brownian motion. They knew a lot about Gaussian processes and corresponding underlying phenomena that you could do with Gaussian processes. And so these Wall Street people began to hire a lot of the physicists from Russia because they had no way of making money. So many of them came over and started to go to work for Wall Street firms because of this ubiquitous application of Gaussian stochastic processes. So there's lots of things that you can do with Gaussian stochastic processes. One of the things we'll show, and I'll end with this. You remember how we showed that if you had a stochastic process, you needed the second and third and fifth and sixth order probability density functions in order to totally characterize it? We will show, and this is a remarkable result, that if you have a Gaussian probability density function, or a Gaussian stochastic process that is so-called stationary, the only thing that you need is the autocorrelation function. And if you have that autocorrelation function, it turns out that all of the probability density functions are defined for that. So you don't need the third and fifth and ninth order probability density functions in these higher dimensions. You only need the one autocorrelation. And from that one autocorrelation, that second order statistic, you can generate all of these probability density functions if you like. We don't have to, but it really shows the power of the Gaussian. And it's a good model to have because it simplifies life a lot. Okay, well, that's it. Yeah, hand in your tests by midnight tonight. And if you want, we can talk more about the tests next time we meet. If there are no questions, last call for, I was going to say last call for alcohol, but that would suggest that I go to bars, which I don't. So last call for questions. Anybody? Okay, thank you very much. Take care.